Hello and welcome everyone to today's lecture. In this lecture, we are going to study characteristics, polynomial, and diagonalization. So let's review some conditions based on what we can check whether a scalar like lambda is an eigenvalue of matrix A or not. If we have A as the matrix, then we say for every matrix we may have one or more eigenvalues, right? So previously we called it by lambda as the eigenvalues. If we consider T as the eigenvalues, all possible eigenvalues, then like lambda, T and lambda is the same, so T can be for more. We know that AV is equal to TV, or we can say that AV minus TV is equal to 0, and these are vectors. Then we learn that even for a scalar like lambda, if it's an eigenvalue of A, then we can say that this V is a non-zero vector, that this condition can be applied. We want to find out set of eigenvalues. So we can say that lambda is an eigenvalue if there exists a non-zero value, that A minus T or A minus lambda in V is equal to 0. Same thing in the previous lecture we had for A minus lambda in is equal to 0. The columns of this A minus T in are dependent if and only if T is in an eigenvalue. We may have multi-solution for this one. It's possible to have multi-solution. The rank of A minus Tin is less than n if and only if A minus Tin is not invertible, which is equivalent that T be an eigenvalue. The determinant of A minus Tin is 0 for T be an eigenvalue. If you want to do that in T is an eigenvalue, then the determinant should be 0. The characteristic polynomial of a square matrix like A is defined as the polynomial obtained by substituting lambda or T for the eigenvalue in this expression. If you want to find out the characteristic polynomial, and if T is an eigenvalue, then we solve the determinant of A minus Tin, which I is an identity matrix, is equal to 0. So we represent it in this way. So the eigenvalues of matrix A are the root of the characteristic polynomial, right? So this is what we have. We call it as characteristic polynomial, and this one we call it as characteristic equation. Then we solve this one and we find out the roots. The roots are the eigenvalues. The roots of this one are eigenvalues. In order to better understand this topic, let's find the eigenvalues and find the basis for each eigenspace. So we will find eigenvalue and basis. In this example, first we need to find out the eigenvalues of this matrix A. And then we will try to find out a basis for each eigenspace. As a reminder from the previous lecture, the eigenspace associated with an eigenvalue is a subspace that consists of all eigenvectors corresponding to that eigenvalue along with the 0 vector. And the term basis of eigenspace, if a set of eigenvectors forms a basis for the domain of a linear transformation, then we call it as the basis. So an eigenbasis simplifies the representation of linear transformation as the matrix representation becomes diagonal. In the previous slide, we learned that this one, A minus Ti, should be equal to 0. So from this one, we have A matrix A minus T of identity matrix 1, 0, 0, 1, which is equal to A minus, and this one will be something like this, T, 0, 0, T, right? Then if you do A minus T, we will have 4 minus T, we will have minus 3 minus 0, which is minus 3, 3 minus 0 will be 3, and 6 minus T will be 6 minus T. Then we need to find out the determinant of this one, right? So determinant of A minus Ti 2, which is this one, minus 4 minus T multiply 6 minus T minus 3 multiplied. And this one can be simplified like minus 24 minus 2T minus T square plus 9, which is equal to T square minus 2T minus 15. And this one can be written as this one, right? T plus 3, T minus 3. T plus 3, T minus 3 will give us the same, T square minus 2T minus 15. Therefore, the root of the characteristic polynomial in this case are minus 3 and 5 for this one, right? So now we need to solve this one. A minus 3i equal to 0, right? So to do this, we have A is equal to minus 4, minus 3, 3 and 6 plus 3, 1, 0, 0, 1 is equal to what? Minus 4 plus 3, minus 3 plus 0, 3 plus 0, and 6 plus 3, which give us what? Minus 1, minus 3, 3, and 9. Then we will find the reduced row echelon form by, for example, we can say this one can be like this: 1, 3, R1 is equal to minus R1, right? 1, 3, 3, 9. Then we can say R2 is equal to minus 3 R1, which will give us what? Which give us 1, 3, and 0, 0, right? If you say R2 minus 3 R1. Because the order of this one is like this, the vector from the general solution will be, for this case, we can do that minus, so the row echelon form, I'll multiply the variables. It will be minus x1 minus 3x2 is equal to 0, and 3x1 plus 9x2 is equal to 0, right? So after the solving like what we did using RREF, you can finally come up with this solution. The general form will be something like this: minus 3x1 and x2, which is a general form. We can say this one can be something like x2 multiply minus 3 and 1. This is a general form for this equation, as we found using the RREF. Therefore, minus 3 and 1 is a base for the eigenspace of A corresponding to this one, and eigenvalue is minus 3. Then, in the same way, we can do for the second one. In the second case, where we have A minus 5, I2 equal to 0, we can do the same. For example, minus 4, minus 3, 3, and 6, minus 5, 1, 1, 0, 0, which give us minus 4, minus 5, minus 3, minus plus 0, we can say 3 plus 0, and 6 minus 5, which will give us minus 9, minus 3, and 3, 1, right? Then if we apply RREF, we can say, for example, this one, R1 is equal to minus R1 by 9, then we will have 1 by 3, and 3, and 1. Then we can make it 0 by multiplication of that one 3 times of this one. Then we will have, like, for example, R2 minus 3 R1, we will have 1 by 1/3 and 0, 0. So in here, like the previous one we did, we come to the general form of x2 multiply minus 1 by 3 and 1. This is what we found here. So next, we found that eigenvalues are minus 3 and 5. Now we want to find out the eigenspace. In the case of minus 3, we reach to the form of minus 1, minus 3, 3, and 9. We solve the corresponding system of linear equation, and we will find that x1 is equal to minus 3t. That we find already. X1 is equal to minus 3t. And x2 is equal to t, where t is any parameter, or you can say constant c that we have. Therefore, the eigenspace corresponding to minus 3 is this one. This is the eigenspace, minus 3t and t. We can say minus 3c, minus 3, anything you want, which t is a member of R. In the same way, we can do for 5, and the eigenspace of 5 is minus 1 by 3t and t. This is the meaning of eigenspace. The eigenvalues of an upper triangular matrix are its diagonal entries. So in here we have an example. This one is a matrix 4 by 4. If you want to find out the eigenvalues, very easy. Minus 3, 6, minus 5, and 8. You don't need to do any calculation. If it is upper triangular, as you can see, the lower part is 0, then the eigenvalues are the main diagonal elements. If a square matrix like A, which is n by n, has n eigenvalues, then the sum of n eigenvalues is called as trace A. Trace A is applicable on square matrices, and the meaning is sum of its diagonal entries. So trace means sum of diagonal components, right? We show it by trace A, as you can see here. And this is rule number 1. Rule number 2 is the product of n eigenvalues is determinant of A. Let's see one example to better understand this one. We have a matrix A, which is n by n, 2 by 2. This is A, right? So we already found that eigenvalues are minus 3 and 5. So what is the trace of A? Sum of eigenvalues. So this one, sum of these two is what? 2, right? So trace A is equal to minus 4 plus 6, which is equal to 2, right? So you can see same. And determinant, how you can find the determinant of A? That's minus 4, 3, minus 3, and 6 is equal to what? Minus 24, minus 9, which is equal to minus 15, right? And multiplication of these two is also minus 15. So sum of n eigenvalues is called as trace A, and product of n eigenvalues is simply determinant of A. These are two rules. the dimension of the eigenspace of a matrix corresponding to like eigenvalue of lambda is less than or equal to multiplicity of lambda. What is multiplicity? I will explain. When considering an eigenvalue like lambda for a matrix like A, the eigenspace associated with this lambda is the set of all eigenvectors corresponding to that eigenvalue. The dimension of the eigenspace is called as the multiplicity of lambda, right? So we can say the dimension of eigenspace is called as the multiplicity of lambda. The algebraic multiplicity of an eigenvalue is the number of times that lambda appears as a root of the characteristic polynomial of A. The fundamental theorem of algebra guarantees that algebraic multiplicity is always greater than or equal to 1. And one thing more, the key relationship is that the geometric multiplicity, like what I say, dimension of the eigenspace, is always less than or equal to the multiplicity of eigenvalue. In other words, if an eigenvalue has algebraic multiplicity like k, then the corresponding dimension is at most k. And here is the example. Find out the eigenvalues 1, multiplicity 2, and the basis for each eigenspace of this linear T, which are 3. So we have this linear operator x1, x2, and x3, T on x1, x1, x3, which is minus x1, 2x1, minus x1, and x3. So we will find out. What is the standard matrix of this T? Minus 1, because we have nothing here, 0x2 plus 0x3. That's why minus 1, 0, and 0. In here we have 2, minus 1, and minus 1, x0, x1 plus 0, x2, so 0, 0, and minus 1. The characteristic polynomial of this one is determinant of a minus ti 3, which is, thus we multiply this one by the this one. So this ti3 will be something like this, t 0, 0, 0, 0, 0, 0, right? If you say a minus this one, you will come up with something like this, and if you want to find out the determinant, then it will be something like this if you do the multiplication, and finally by simplification we will come to the minus 1 minus t cube, which is minus t plus 1 cube. In this case, the only eigenvalue of t is minus 1 and the multiplicity is 3. The eigenspace of t corresponding to minus 1 is the solution of a plus i3, x is equal to 0, right? And if we apply the RREF, we will come up with something like this, 1, 0, minus 5, 0, 0, 0, 0, 0, 0. Then based on this, we see that the basis of eigenspace is minus 1, which give you this basis. The next topic that we need to learn here is diagonalization of matrices. Matrix diagonalization is the process of transforming a square matrix n by n matrix into a diagonal matrix. You remember that diagonal matrix is a matrix where the components on the main diagonal are non-zero, but the rest are all 0. Right? The rest are all 0. But this one can be 1, 2, or anything, right? So identity matrix is a diagonal matrix. To do so, in order to convert one matrix, a square matrix, to a diagonal matrix, we use eigenvalues in eigenvectors. So in order to do this, we have to follow some steps. First of all, we need to find out the characteristic polynomial. So 1, this is the first step. Then we need to find out eigenvalues, and also for each one we need to find out eigenspaces. If the matrix is diagonalizable, we construct P using the eigenvectors as columns and matrix D as the eigenvalues of the diagonal. We call this a matrix diagonalizable if A is equal to P D P inverse, where the D is a diagonal matrix and P is invertible matrix. So this is diagonal and P is invertible. And here you can see it's invertible. So A equals P multiply D multiply P inverse. The matrix 0, 1, 0, 0, we want to check whether it's diagonalizable or not. It seems to be not. Why? In order for a matrix to be diagonalizable, it must have n linearly independent eigenvectors, n number of column, rows, and column, linearly independent eigenvectors. What do you think? Do we have or not? So in this case, A has only one distinct eigenvalue, which is 0, which is 0, and the multiplicity is 2. So it lacks sufficient linearly independent eigenvectors, and we say it is non-diagonalizable. In other way, so we have to find out P as invertible matrix and D as a diagonal matrix, right? Because A is upper triangular, the only eigenvalue is 0, and its multiplicity is 2. So the diagonal matrix D must be D equal to 0, and therefore this one, A is equal to P D P inverse is, that's why it's not diagonalizable. We will have more examples to understand the concept. Here is 3 by 3 matrix. First, we need to find the characteristic polynomial. This is what we do. A minus T identity. T identity in this case is what? T. Right? A minus this one will be minus 1 minus T, 0, 0, 0, 1 minus T, 2, 0, 2, 1 minus T. And if you do the determinant, as we did already, finally you come up with something like this one, right? Something like this one, and the calculation is here. We do this one by the determinant of this one, finally we come here. Based on this one, the eigenvalues are minus 1 and 3. Minus 1 and 3. Then we will find the eigenvectors corresponding to these eigenvalues. Based on what we already studied, we can find that in the case of 3, the base will be, because the multiplicity is 1, so if lambda is 3, then we can say that it will be 0, 1, 1, 0, 1, 1. And in the case of lambda is equal to minus 1, then it will be 1, 0, 0, and 0, 1, minus 1. So we can write them together, as you can see here, as the basis. This seems to be linearly independent. In the case of matrix P, the column I of matrix P is eigenvector number 1. Eigenvector number I. It means what? This one will come here, this one will come here, and this one will come here. Then we need to find out D. So for the D matrix, at row I, column I is the eigenvalue number I. Row I, column I, right? We get the eigenvalue. It means we get 3 here, minus 1 here, and minus 1 here, because the multiplicity of minus 1 was 2, and the rest is 0. So this is the diagonal form of this matrix. First, we check whether it is diagonalizable or not. If yes, then we can find out in this way. If you want to check whether it's okay or not, we should do something like this. A equals to P dP inverse, right? So what is P? P is this one. 0, 1, 0, 1, 0, 1, 1, 0, minus 1. Multiply D, 3, 0, 0, 0, minus 1, 0, and 0, 0, minus 1. If you do matrix multiplication, the result of this one will be something like 0, minus 1, 0, 3, 0, minus 1, and 3, 0, minus 1. Then this one, multiply the inverse of P. The inverse of P will be this one, 1 by 2, 1 by 2, 1, 0, 0, 0, 1 by 2, minus 1 by 2. And multiplication of these two will give you A. It means the calculation is okay. I already explained how to do matrix multiplication. I already explained how to find the inverse of P. So if you multiply P, multiply D, multiply inverse of P, you must get A. Then it's diagonalizable. Now we want to check whether a matrix is diagonalizable or not. Based on the definition, in n by n matrix, square matrix, A is diagonalizable if and only if two conditions are satisfied. The total number of eigenvalues when each eigenvalue is counted as often as its multiplicity is equal to n. It means what? It means we count the multiplicity of each eigenvalue. If the multiplicity of eigenvalues is equal to n, this n, then we say it is diagonalizable. And for each eigenvalue, we go for dimension. This is called as dimension. Then dimension corresponding to eigenspace, which is based on n minus rank, a minus lambda in, is equal to multiplicity of lambda. I will give you example to better understand the concept. Example is here. this is diagonalizable, and we will find the diagonal matrix. We want to check whether this matrix is satisfying the condition of being diagonalizable or not. Again, we will go for determinant of A minus DI3, and based on the calculation that we already did, it will become something like this. Now, in here, we have two eigenvalues. One is -1 and the multiplicity of 1. You remember, multiplicity is the number of occurring one eigenvalue. And eigenvector for this one is -1, 0, and 1. Then also we have -4, which has 2, multiplicity of 2, and 2 eigenvectors we have. One is -1, 1, and 0, and another one is -2, 0, and 1. So this is a diagonalizable matrix if and only if dimension of the eigenspace corresponding to eigenvalues is 2. So based on that one, we can check that 3 minus rank B minus -4 I3 is 3 minus 1 is equal to 2. That's why B is diagonalizable. And in order to find P and D, so we will bring this one here, and this one here. This is P matrix, and -1 here, -4 here, because it is 2 times. This is the way how we can find diagonalization of a matrix. Please practice and feel free to ask me if you have any questions. Thank you.